Okay, so first section we're going to look at is section 3.3, which is on the factor theorem. And a lot of factoring has to do with dividing to figure out the factors. So some of the things that we're going to do with polynomials, I'm going to show it to you with basic numbers. So you can kind of get the idea of how it would work, and then we'll do it with polynomials. Okay. So remember that if an equation, if you're looking for the roots of an equation, you're looking for the zeros. Okay? That just means you're looking for a number that you can plug in for x and get 0 for y. Okay? And this last one here, IFF, that's an abbreviation for if and only if, which if you remember from geometry, that's a statement that can be read forwards and backwards, and it's true both ways. So this last one basically says, if a number is a root, then you can plug it in and get 0. Or you can say, if you have a number that you plug in and get 0, then that number is a root. So you can read that statement forwards and its converse. They're both true. Okay, that's IFF. So, sometimes to figure out if something is a factor, right, we're going to use long division. Right? Now, when you're doing quadratics, it's a little easier to factor because you can write the two sets of parentheses and then you can FOIL it and check it. Well, with cubics, it can be a little harder to factor. So, I'm going to show you something with numbers first, and then we'll look at it with polynomials. So let's say I gave you something to factor. Okay, something very simple, the number 12. Okay? And I'm going to tell you 3 is a factor. So now you know one of the factors of 12. I want you to find the other one. How could you figure out the other factor of 12 knowing 3 is a factor? Yeah?
Divide 12 by 3?
Yeah. You take what you're trying to factor and you divide it by what you know is a factor, and that gives you the other factor. Right? So this idea is very simple with numbers. Right? If you know 3 is a factor, you're saying 3 times something gives you 12. How do you solve for something? Exactly what we just said. Divide by 3. And then you have something by itself. So 12 divided by 3 is 4. Right? So 4 is the other factor. Okay. So now if I wanted to factor the number 12, knowing that 3 was a factor, and now I figured out 4 is a factor, I would write 3 times 4, and it gives me 12. The key that's going to be very important is the way you can figure out something is a factor is you divide it, and it goes in evenly. You don't get a remainder. And that's going to work the same with polynomials. If we divide something into something, and we don't get a remainder, then you just found a factor. If you get a remainder, then you didn't. So no, it seems very, very simple, but it's going to be the same idea with polynomials. So one thing we're going to want is there a quick way to find remainders when we do division? Maybe we don't care about the quotient. If all you're caring about is this a factor of that, all you have to know is what would the remainder be when you divide them? And there is a quick way to find remainders without actually going through doing division, right? And I'll show you what that is for polynomials. It's another way of saying the same thing I just said. If you divide two things and get a remainder of 0, then you know what you divided by is a factor. I'm going to just say that. Now, factoring a polynomial, why we would end up doing it, is it makes it very easy to find the roots. Okay? If I gave you this, let's say, and I said, what are the roots? Quick. So it's not so quick sometimes. Took maybe at least 5 seconds for someone to raise their hand, but yeah, what are they?
-2.
Nope. But this is good because this is why we actually factor it, because this is not super quick to figure out. Tried to make this up to be nice numbers. Yeah, you want to try again?
-4.
And?
-1.
-1. If I had given it to you like this, plus 1 plus 4, I bet people could look at that quicker and say, oh, -4, -1, right? It's easier to see the roots if you can factor it. And that's what we're going to try to do with ones that are a little more complicated than quadratics. Okay, so let's try that same idea of dividing to figure out if something is a factor with polynomials. All right, so what I can do is, actually, you know what? I'll give you a step, and then we can do it in a problem, and just so you can kind of see it as we go. But the first step is, if your polynomial is missing any terms, you have to make sure every term is represented. So if it's missing one, fill in a 0 for that term. Okay, and the dividend, that's the thing that would be like on the top of the fraction. Or if you were making a long division symbol, that's the thing that's on the outside. I'm sorry, inside. Sorry. So dividend, gonna go right there. Okay, so let's look at our problem, and I think we have 4 steps. 5 steps. I think the 5th step is just to repeat until you're done. Let me see. Bring down the next term and repeat until you're done. Yeah. Okay. So I would leave, all the steps are about that long, so maybe leave however much room it took you for that. I'd leave like 5 or 6 lines so we can put in the other steps. And let's start to look at this at the same time. So the first step said make sure that your dividend, this, is not missing any terms. Am I missing a term there?
Yes.
Yeah, which one?
X
To the second. So the first thing I'm going to do is write it like this. If you don't do that, you're not going to have, you have to line up like terms here. If you don't do that, you're not going to have a column for the squared terms. Now you do. Okay. So we've got the cubed, squared, linear, constant. Perfect. So now this problem is ready to go. All right, so step 2. Divide the first term of the divisor into the first term of the dividend. So basically take the first term on the outside and divide it into the first term on the inside. Let's try that. First term on the outside. Derek, what's my first term on the outside?
Are we talking about, so x minus 3?
That's the outside, yep.
X.
X. And what's the first term on the inside?
X cubed.
X cubed. You're going to divide this into that, and we're going to put the answer right on the top. Okay, so Skylar, what do you get if you divide x cubed by x?
Is it 3? No.
So remember x cubed, and then divide by x.
2x.
So these are going to cancel, and what's x times x?
Squared.
X squared. Okay. So you get x squared. And that's it for step 2. Any questions on that step? Okay. So now, 3rd step. Multiply the answer that you just got from, that's actually step 2. Multiply the answer that we just got in the 2nd step by each term on the outside, okay, the divisor. And this is where you have to line up like terms. So put the result under the appropriate term. What I'm saying is just line up your like terms. Okay, so multiply the answer that we just got by each term on the outside and put the answers under the like term columns. Okay, so this is going to be kind of like a distributive property. We're going to multiply something that's on top by however many things we have out in front. Okay, in my case, I only have two. I have an x and a minus 3. Okay, so let's look at that. Or, yeah, x and minus 3. So we'll start with that. Peregrine, what's x squared times x?
X to the third.
X to the third, and we're going to put it in the x to the third column. Sam, what's x squared times negative 3?
Negative 3x squared.
Yep. And now you can see why we had to put in the 0x squared, so we had a column. Okay, that's it for step 3. Questions on that? All right, so we do that. And when you're doing regular long division, what's the next step usually? Divide, you multiply, subtract, and then you bring down. So now we're going to subtract. That's actually step 2. So subtract the columns that you just did in the last step. Okay, so subtract columns from step 3. Now, when I subtract, I usually go like this, so that I remember to subtract everything. Chris, what's x cubed minus x cubed?
0.
0. That should always happen if you did these steps correctly. Each time you divide, your highest exponent should drop off. So now you should be left with an exponent that's one smaller, at least one smaller. Sometimes a couple things drop off if you're lucky, but you're going to have at least one thing drop off. So now we should not have cubed terms anymore. All right, so 0x squared minus negative 3x squared. What's that going to be? 3x squared. Okay, so that's step 4. And now step 5 is bring down the next term and keep repeating this process. How do you know when you're done? Well, the degree of your remainder has to be less than the degree of your divisor. Then you're done. So the degree of the remainder has to be less than the degree of the divisor, the thing on the outside. Okay, so let's look at what the degree is now of our remainder, and then let's compare it to the degree of the divisor. Let's see. Okay, right now I bring down my next term. Even before I brought it down, my degree is 2. What's the degree of the x minus 3?
1.
It's 1. So we got to keep going till the degree is less than 1. Well, if you have a degree less than 1, that basically means you're going to end up with a constant. You're going to end up with a number remainder here. Degree 0. All right, so now let's divide the first term here into the first term here. Do it all over again. How about, yeah, what do we get?
Would it be plus 3x?
Yep, plus 3x. So 3x squared divided by x gives you 3x, and we're going to check it by multiplying it back out. It's kind of part of it. 3x times x, 3x squared. Kayla, what's 3x times negative 3?
9x. Oh wait, no, negative 9x.
Negative 9x, yep. Okay, so we divided, we multiplied, now we're going to do subtraction. Riley, what's 3x squared minus 3x squared?
Nothing.
Okay, that's gone. Negative 8x minus negative 9x. X. What's the degree on my remainder now? 1. It's a degree 1. That's a degree 1. So we got to go one more time. Okay. So bring down my next term. And now x goes into x how many times? Once. If all you wanted is the quotient, you're done. That is the quotient to this problem. x squared plus 3x plus 1. If you want the remainder, we got to finish up. So 1 times x, let's see, 1 times negative 3. And some people look at that quickly and they're like, oh, it cancels. Plus 3 minus 3. Remember, you're subtracting. So you really, you get a remainder of 6. And that's, now you know you're done because the degree on that's a constant. The degree of a constant is 0. And that is less than the degree of what was on the outside.
What does the remainder mean for the problem?
So this remainder means that this does not divide into that evenly. So what does that really mean? This is not a factor. If you were trying to factor x cubed minus 8x plus 3, x minus 3 would not be one of the factors you should be using. It didn't work. All right? So there's a couple ways we can write our answer. We can write quotient and remainder. So the remainder was 6. Quotient, x squared plus 3x plus 1. That's one thing.
No, you would write not a factor.
If the question was, is it a factor? Yes. This just said to divide. So just divide.
Okay.
And just tell me quotient and remainder.
Okay.
Now, another way you can write the quotient and remainder, think about like if you had numbers. Let's do 12 divided by, let's do 13 divided by 5. What's the quotient when you do that? 2. What's the remainder? 3. So you can write your answer this way. 2 plus, remainder is 3 over your denominator. It's 2 plus 3/5, or we could say 2 and 3/5. Quotient plus remainder over what you divided by. Any question on that?
So you can do that with the top one.
You can do that exact same thing here. The answer is quotient, x squared plus 3x plus 1, plus remainder, 6, over what you divided by, x minus 3. That's the same thing. What's nice about the one that I wrote here is you can check it.
Which one?
The one that I circled on the right-hand side. I can type that in. And watch what happens. I'm going to type in x squared plus 3x quotient plus, in parentheses, remainder over what I divided by. And I probably need an extra parenthesis right there. Okay, so we had that. And now let's type in the original problem. X cubed minus 8x plus 3. Alright, so we got x cubed minus 8x plus 3. And what did I divide by? X minus 3. Now, when I graph those, they should come out exactly the same. Right? Because that's the original problem. y2 is what I think my answer is to the original problem. So let's graph it and see if they look the same. We don't really care what they look like, just if they look the same. Yeah. Since they look exactly the same, we probably did it correct. Right? Graphing never proves you did it correct, but it is a way that can suggest you did it correct. Any questions on writing your answer either way? Yeah?
Okay, what is the remainder used for? And if we're ever looking for just remainder, can we just skip to the end of the problem and just divide like the last two terms?
Well, there's no way to use long division and just kind of skip somehow like to this part of the long division because you can't get there without doing everything else. But there is a way to find the remainder without doing this at all. Yeah. So I'm going to show you that. And the remainder is used to determine if something is a factor. That's the important thing. This is not a factor. X minus 3 is not a factor of that. So if you were factoring it, you don't just keep guessing. Like, all right, x minus 3 didn't work. I'll try x minus 2. I'll try x minus 1. I'll try x plus 6. There's a way you figure out what you should try. But that's later on. Okay, let's try this one. So this time we have a trinomial that we're dividing by. And we were missing a few terms, but I had already filled in the zeros for those. Okay, one thing we're going to notice about long division is you kind of need a lot of room down and to the right. That's kind of how these problems work. So you got to leave plenty of space to go to the right. Okay, so step 1 is already done. Unless we're missing anything else I didn't fill in. Nope, we're good. So divide first term on the outside, 2x squared, into 2x to the 4th.
X squared.
We're going to get x squared. Multiply it back out. What's x squared times 2x squared?
2x to the 4th.
2x to the 4th. X squared times x. Positive x cubed. X squared times 1 is just x squared. What are we going to do with all that? We're going to subtract. Okay, so here we got 2x to the 4th is gone. Negative x cubed minus x cubed. Some people say, oh, negative positive, but not really. It's negative x cubed minus x cubed. So it's minus 2x cubed, and then 0 minus x squared. Bring down the next term. Okay, the degree on my remainder right now is a 3. Degree on my divisor is a 2. I got to keep going. What's negative 2x cubed divided by 2x squared? Negative x. Multiply it back out. That's negative 2x cubed. What's negative x times x?
Negative x squared.
Negative x squared, and negative x times 1.
Negative x.
Negative x. Actually, this step is going to be kind of nice. I told you sometimes you get two things that cancel. Watch what happens here. What's negative 2x cubed minus 2x cubed? 0. What's negative x squared minus negative x squared?
0.
So we just got two things that canceled in the same step, and now we're going to be done. Okay, because watch what the degree is going to be. 0 minus x is plus x. And now bring down the 2. So this whole thing, that's your remainder. X minus 2. Okay. You can't divide 2x squared into x now. It won't work. Okay, it won't work.
So once the degree is lower, then that's the remainder.
Yep. So the degree on my remainder is a 1. The degree on my number on the outside here is a 2. I'm done. So quotient is x squared minus x. Remainder, x minus 2. Or you could write the answer the other way. The way you could type into the calculator and check it. So quotient plus remainder over 2x squared plus x plus 1. That'd be a little messy to type in. I'd need a lot of parentheses, but I could do it. Any question on? Yep.
So the remainder could be like as long as necessary, really?
Yeah. Yep. It depends on the problem. Yeah. In general, I'm not going to give you ones that are much worse than that for remainders. But yeah. Okay, so I'm going to do this with I'm going to pick some numbers first, and then I think it'll make sense when I do it as a polynomial. All right. So that's a formula that's always true. Right. So if you let f of x, let's say, be the number, actually I'll do the example I did before. Let that be 13. Let h of x be 5. When we did that, the quotient was 2. And what was the remainder? 3. Let's check and see if you actually plug those numbers in, does this work? I'm saying 13 equals what I divided by 5, times my quotient. My quotient was 2, and my remainder was 3. Is that true?
Yes.
Yeah. It's basically, it's just a way, when you do long division, then you usually check your answer. You take what you divided by, times your quotient, add your remainder, and see if it equals your numerator. If it does, then you did it correct. Okay. But you can do exactly the same thing with polynomials. It's a little messier to multiply it out. It's not as simple as just 5 times 2, because you'd have to do a lot of foiling. Okay. But I just want to keep this formula in mind. Okay. We're gonna use that. Okay, so remember that the degree of the remainder, and we already wrote this, I'm just kind of writing it again, is always less than the degree of the divisor. It has to be. The degree of the remainder is always less than the degree of the divisor, or you don't even get a remainder. We might try one of those later on. Okay, if the remainder comes up 0, then you're also done. Okay. But both the problems we've done so far had remainders. Now, think about this for a second. If we divide something by a linear polynomial, okay, linear would be something like this, x minus 3, or x plus 2. Okay, no, don't divide by something that's like x squared. Okay, just an x and just a number. We just said that when you divide, the degree of the remainder is less than the degree of this. Okay? What's the degree of something that's linear? 1. And the remainder, when you divide by something, has to be less. So what's less than a degree 1?
0.
A constant. So anytime that you divide by something linear, the answer is always a constant. It's just a number. And I gave you guys an example of that one right here. You divided by something linear, and the remainder was just a number, just a 6. Okay, that's always true. Now here, we divided by something that was quadratic. So no, your remainder is not going to be linear. It's going to be 1 degree smaller than that. But that's not a constant. Okay? So any questions on that? If you divide by something linear, the remainder is just a number. No variable. So let's look at basically this formula, right? But I'm going to make it a little bit more specific. Instead of saying I'm just going to divide by anything, okay, like h of x, I'm going to put something linear right there, specific, okay, something that's always linear. Right? So I'm going to take my formula, that's my numerator, and I'm going to divide it by something linear. Exactly what? I don't know. Just say it could be x minus 5, it could be x minus 10, it could be x minus minus 7, which would really be x plus 7, but you're going to divide by something linear. Okay. So now, if you did that, you would have that. Your numerator equals what you divided by times your quotient plus your remainder. I'm just saying right here, I'm not dividing by something random. Okay, I'm dividing by something linear. Okay, and what we're getting at is a quick way to find the remainder. Any questions why this formula is true?
Wait, so this is to find the remainder?
That's what we're getting towards, yep. It'd be great if I just had a formula with r all by itself on the right. Something equals r. And that's what I want. I want a way to just get the remainder. Okay? But here's what we're starting with. Now, does anybody see what I could plug in for x? and you would end up with just an r by itself on the right-hand side. Yeah, and that's a little trick. Okay? If you plug in c, you take this number and you plug it into f of x. F of x is the formula that's in the top. Okay? So you take the number after the minus sign and plug it into the top formula. This is what you get. Right? So I'm saying let x equal c. Plug in c for x. You're going to get this. Right? F of c, because you're plugging in c for x. And here you get c minus c. That's where something special happens. Okay? But remember, you can't just plug in c here. You got to plug it in everywhere there's an x. So you're plugging it in here, 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 and then the remainder, well, that's a constant. So there's nothing to plug in there. What happens when you do c minus c times q of c? You get 0. This part disappears. And now you have a formula to find the remainder. And the trick is basically take what you're dividing by, plug in the number after the minus sign into the top, and magically it just gives you r. It will just give you the remainder without having to do all the division out. Okay, and that is the remainder theorem. So if you have something and you divide by something linear, okay, this only works if you divide by something linear. So like example 1. This would not work for example 2. Okay. If you divide by something linear, the remainder is found by taking what you divided by, the number after the minus sign, and plugging it into your numerator. So I'll go back to our first problem and let's see if we can get a remainder of 6 doing this very quickly.
So this you'd use this for a problem where they're just asking you to find the remainder?
Yeah. Okay, so let's say they wanted to know the remainder here. I am dividing by something linear, 3. What's the number after the minus sign? 3. Now keep in mind what we should get for a remainder. We should get 6. So take the 3, plug it in for x. 3 cubed minus 8 times 3 plus 3. What's 3 cubed? 27. 8 times 3? And what's 27 minus 24? 3. And what's 3 plus 3? 6. So very quickly we got the remainder. Now if you want the quotient, then you got to do all that other stuff. Okay, but if you only want the remainder, you just have to take the number after the minus sign and plug it into your numerator. Okay, and that's a little trick based on the formula I just showed you. It just cancels everything out and it just magically gives you the remainder.
So the number's always going to be positive?
Well, it could be, we're going to do one of each. So all I want here is the remainder when you divide f of x by this first, and then a separate problem dividing by g of x. Okay. So let's start with dividing f of x by h of x. So f of x divided by h of x. Okay, the remainder. Am I dividing, is h of x linear?
Yes.
Yes, it's not like it's x squared, that messes everything up. So it's not x squared or anything like that. Is it of the form x minus a number?
Yes.
Then I just take the number after the minus sign, which is a 3. And we're going to plug that into our numerator. Okay? So we're going to get 3 cubed minus 2 times 3 squared plus 3 minus 5. 3 cubed, we just did that. 3 squared is 9 times 2 is 18. What's 27 minus 18? 9 plus 3 minus 5. So we get 12 minus 5 or 7. Double check my arithmetic, but I'm pretty sure we did that right. So that's the remainder. So again, the it's not a 0. Okay, I'm really looking for remainder of 0 when we start to look for factors, that's what we're building towards here. Okay? So no remainder 0 there. So x minus 3 is not a factor of f of x. Okay, let's try doing f of x dividing by g of x and finding the remainder. Okay, am I dividing by something linear?
Yes.
Yes. Is it of the form x minus a number?
No.
No. Then we need to think of it that way. How could you think of it as x minus a number?
X minus -1.
Yes. So now you think of it that way. And you say, okay, what's the number after the minus sign? -1. So now you're plugging in -1 for x. So you got to be careful when it's a plus. You can still use it, but you got to think of it as the number after x minus. So write it like this. Whatever's in that box, that's what you use. Okay, whatever's in the box. So -1. Okay, let's see what we got. So -1 cubed, 2 times -1 squared, -1 minus 5. Okay, -1 cubed gives me how much? -1 squared times -2. -1 minus 2, -3. -3 minus 1, -4. You get a remainder of -9. Again, double check that I didn't make a mistake, but that's the idea. Any question on that? So you could give me some huge thing like x to the 48th minus 3x to the 37th. I'm not going to write everything out. And you could say divide that by x minus 2 and just tell me the remainder. Well, it's easy to do it this way. All I got to do is plug in 2 for x and just see what it comes out to. Now, if you were to try to do this with long division, you got to fill in all the zeros, right? 0x to the 47th. So you're going to have 48 variable terms plus the constant at the end, the minus 5.
What you do in your weekends.
And then you're going to have to do all the division. There's a much easier way to get the remainder. Okay? I wouldn't ask you to do a quotient like that anyway, but I might ask you for a remainder in a problem like that. Because the remainder is very, very doable. But any question on that? Okay, so that's the remainder theorem. All right, so let's look at this. So if f of x is divided by x minus c, then this is basically the formula I just gave you right here. Right here. Except now we have a formula for the remainder. We know r equals f of c. So I basically just substituted that in right there. And that's why it'll say x minus c q of x plus f of c. Okay, just remember, f of c is just a fancy way of saying remainder. That's all that part is. Now, suppose that the number you have for c is a root. What does that mean about it? If a number is a root? It means it's a 0, right? It means it's a root of the equation. So what that means is, if you have a number that's a root, you can take that number, plug it into your formula, and get 0. All right, so keep that in mind. You can take that, plug it in, and you get 0. So far, that's never happened for us. We've plugged the number in, and we've always gotten a number remainder. We've never gotten 0. So, according to the remainder theorem, if f of c equals 0, this part right here basically drops off. You don't have it anymore. If the number c is a root. If it's a root, the remainder would come out to be 0. Any question on that? All right. So, what that basically means is that gives us what's called the factor theorem, right? If a number is a root, that means you take that number, you plug it into your function, and you get 0 for the remainder. So that's all that the factor theorem really is. It's kind of like the remainder theorem, except you're always saying the remainder would be 0. Okay, that's what the factor theorem is. Okay, so f of x would be your numerator. You're dividing by x minus c. And if x minus c is a factor, then that means this number has to be a root. It has to be. Okay, and I wrote this as IFF, meaning you can read it both ways. Right? If you have a number that's a root, then you can also work backwards to figure out what the factor would be. So if I told you 3 is a root to a polynomial I'm thinking of in my head, then you would know that must be one of the factors to what I'm thinking of in my head. Right? So it works both ways, and we're going to try it both ways. I think the last problem I give you, I say something like, I'm thinking of a polynomial that has roots of, and I make up 3 numbers, 2, -5, and 3. What is my polynomial? So you've got to figure out the polynomial that has those roots. Okay? And the factor theorem lets us do that. Okay, so let's use the factor theorem to show x plus 2 is a factor of x cubed plus 5x squared plus 5x minus 2. Okay, so to show something is a factor, all we need to really show is what? Show that when you do the division, you get a remainder of 0. Do we actually have to do the division to prove the remainder is 0?
No.
No, we can use the remainder theorem. And when you use the remainder theorem and get 0, it's called the factor theorem. It's basically the same thing. All right. So, what am I going to plug in for x in that formula?
-2.
Remember, you're thinking of it like this. Whatever's in the box, whatever comes after the x minus, that's what you're plugging in. Okay, okay, let's see what happens. So -2 cubed, 5 times -2 squared, 5 times -2 minus 2. Let's see what we get. What's -2 cubed? -2 squared times 5, 20, minus 10 minus 2. What's -8 plus 20?
12.
12 minus 10 minus 2. 12 minus 10 is 2. 2 minus 2 is 0. So we get a remainder of 0 when you divide what's circled by x plus 2. So what does that mean if you get a remainder of 0? It's a factor. So if you were going to try to factor this, one of the factors is x plus 2. Okay, any question on that? Now, I'm not going to try to factor that today, but remember when I said, all right, 12, and I wanted you to factor it? And I told you that one of the factors was 3. How did you find the other factor? You divided it. Right here would be the quotient of 12 divided by 3. So you do that off to the side, and say, oh, that's 4. There's your other factor. You can do exactly the same thing here. We know that this equals something times something. One of them is x plus 2. What's the other one right here? It's the quotient. It's the quotient of what's circled divided by x plus 2. And once you do the quotient, you could figure out how it factors. Now, there is a quick way to do the quotient. We're going to learn that tomorrow. Okay? And the quick way would actually, yes, it would work here. Okay? It doesn't always work, but it would work in this one. Okay. But any question on why we got remainder 0?
So that would be a factor.
Yep, that would be a factor. Yep. We don't know the other factor yet, but eventually we will. Okay, so I've said these a lot. Let's see if you guys can kind of remind me some of the things that are the same. Okay, let's say I have a number c, and I know that it's a root. What's another way of saying that?
C equals 0.
F of c equals 0. If you plug it into your formula, you'll get 0. What else? Think visually. Yeah? It's an x-intercept. What else? So we said c is a solution. If you plug it in, you get 0. It's a 0. It's a root. We've said that before. It's an x-intercept. But this one is important, the fourth one. It's what enables you to go backwards if you know the roots and you want to figure out what is the equation that has those roots. So if a number is a root, x minus that number is a factor. Okay, that's what you want to keep in your head. If a number is a root, x minus that number is a factor. And we kind of proved, or we did an example with that right here. -2 is a root to this polynomial. So x minus that is a factor. Okay? And we proved it was a factor because we got a remainder of 0. Yeah.
So you only know that if you do it out and you get 0.
Yeah, you only know if x minus something is a factor if you do out the remainder theorem.
Okay.
But that's still quicker than having to do long division.
Right.
Yeah, much quicker. Okay. Any questions on any of those equivalent statements? They all mean the same thing. Different ways of saying the same thing.
I'm so confused on why x minus c is a factor.
So you agree here that we showed that x plus 2 was a factor, right? And that's because, well, do you agree that x minus -2 is the same as x plus 2?
Yes.
Okay, so we showed that x minus -2 was a factor. Right? Now, if you take -2 and plug it into the formula, what did we get?
Oh, just 0.
We got 0, all right? Which, if you plug a number into a formula and get 0, that's the definition of it being a root.
Right.
So, if this number is a root, okay, and we showed that it has a remainder of 0, that ties in with the factor theorem. If you get a remainder of 0, that proves that you have a factor.
Oh, so it's like with the top part where it was x minus -2. Like
Yep.
that equals.
Right.
Is that what you're saying?
Yeah, if you can prove that this number is a root, meaning you plug it in and you get 0, it shows it's a root, and we know that if you plug in a number and get 0, this is also the remainder. So if you divide something and get a remainder of 0, it automatically means it's a factor. Automatically. If you got a remainder of 1, then I would say no, it's not a factor.
So it's just saying that like if it's a root, then x minus c is a factor.
Yes.
Okay, so it's not like an always, because there can be times when x minus a number is okay.
Yes, and we did some earlier in the notes where we got a remainder of 7 or something different. Yep. Okay. So it works the other way. If you have a number that you plug in and you don't get 0 as a remainder, then x minus that is not a factor. Okay. You've got to get 0 for it to be a factor. So let's finish up with these two. So I want you to find a third-degree polynomial that has these as zeros. -2, 1, and 3. Now, there's a lot of different ways to say this information. Okay, I'm just going to use the -2. If -2 is a 0, it means -2 is a root. That doesn't really help me. It means that -2 is an x-intercept. That doesn't really help me. It means that if I plug -2 into some formula, the answer comes out to 0. That doesn't really help me. It's the fourth one on the other page that helps me. If -2 is a root, then what has to be a factor? X plus 2. Okay? These are going to be your factors. Now, some of them may change to x plus. It depends on the roots. But if -2 is a root, x minus that is a factor. What about if 1 is a root? What would be a factor there? X minus 1. And if 3 is a root? X minus 3. So now I'm just going to make that into a plus. And we have to do that out to get our answer. So we get x squared, what's that going to be? Plus x minus 2 times x minus 3. And now distribute all that out. What's x times x squared? And then x times x squared. And Vinny, how about x times -2?
-2x.
Yep. And now multiply everything by -3. And combine like terms. Sorry. That's right. Okay. So x cubed, nothing to combine. And what do I get for the rest of it when I combine all my squares, linear terms, and constants? Yeah, Hager.
I got -2x squared minus 5x plus 7.
Let's check it. -3x squared plus x squared. -2, like it. -2 and -3 is -5 and plus 6. Looks good. Okay. Now, if we graph that, we should already know exactly where that's going to cross the x-axis. It should cross in those 3 spots. Before I graph it, was there a question? Yeah.
Well, so that's your way of checking it, right? Plugging in the numbers or graphing it.
Yeah. So let's graph it. So we've got x cubed minus, let's try again, minus 2x squared minus 5x plus 6. Now, if it doesn't cross where we expect it, we either foiled it out wrong or we typed it in wrong. Does it look like it crosses where it's supposed to? -2, 1, 3. Yep. Okay. So any question on that? And it's a degree 3 polynomial, x cubed. Okay. So now let's see if we can finish up by finding the roots of this equation. Now, a cubic normally wouldn't be something you could factor unless it works out special. And I gave you a hint here to use factor by grouping, so something special will happen. Is that set up to use factor by grouping? Like, is it in the right order?
Yes.
Yeah, I mean, with factor by grouping, you just have to make it so the first 2 terms have something in common, and the last 2. There might be multiple ways to do that. What do the first 2 have in common? Okay, and if you factor that out, what are you left with? X plus 2. So now the whole goal is to get another x plus 2. That's how factor by grouping works. What could I factor out of the second set to make that happen? -4. Because -4 times x is -4x. -4 times +2 is -8. Okay. Now you factor out what this term and this term have in common. What do those both have?
X plus 2.
They both have an x plus 2. If you factor it out of the first one, what's left in the first box? Just x squared And if you factor it out of the second box, what's left? A -4. And you can check it by distributing. Take that, multiply it to that, you get x squared times x plus 2. Multiply -4 times the box, and you get -4 times x plus 2. Right. Now, what would I do with each of those factors? And what do you set them equal to?
0.
Yep. So set them equal to 0.
And x equals 2 and -2.
So here we're going to get -2. And what about over there?
You get
2 or -2.
2 or -2. So how many roots does this problem have?
3.
It has 3, but one of them is what we call a repeated root. So you saw what happens when you had 3 distinct roots. Watch what happens when you have a repeated root. Okay, and this kind of thing happens a lot. So we got x cubed. Let's just change this one. Make it plus 2x squared minus 4x minus 8. So remember, what's the repeated root here?
-2.
-2. Okay, so -2 is a repeated root. So what do you notice at -2? It hits it, and then it kind of bounces away from it. Okay? That usually is what happens with a repeated root. It won't actually cross through the axis, because if it crossed through, then you'd get 2 answers, where it crosses through up and then the way back. But here we just get a repeated root at -2. So you'd still say that there's 3 answers. But -2 is a repeated root. Okay. Any question on that?
I have a question further up a little bit. So when you're taking like the x squared minus 4 on the bottom there, so you include the sign from -4?
Yeah, this negative comes from right here.
Okay, because you didn't include it in the box, so like I don't know.
So,
Like if that was plus,
And you have.
like if this was a plus,
would it be x squared plus 4?
Yeah.
Oh, okay. You just include the sign.
yeah, if that was a plus, then that would be a plus.
Okay.
And then actually that would work out kind of weird now, because now you'd have x squared equals -4, and now you'd be trying to take the square root of -4, which would be imaginary. So you would only get one answer, and the graph would look more like this. It would cross the x-axis in one spot. It would never really turn. Yeah. So, and we're not going to get into it too much, but technically this problem would still have 3 roots as well. You would now say 1 real, 2 imaginary. The imaginary ones you can only get by using algebra. You can't get them on the calculator because the calculator only shows you the real. Yeah, now we're back. Okay, any question on that? Is there any question? I think we've done that before, about how to use a graphing calculator to find the zeros.
Yeah.
No question on it? Okay, you just second calc, that's how you gotta do. This is probably one that wouldn't easily be factorable. That's why they said use the calculator. Okay. So that's the homework for tonight on 171. So it's 1, 2, 4 through 6. And then actually I could probably just simplify that and say 9 through 21 odd. I must have erased some that changed it. So why don't we just say 9 through 21 odd? Instead of writing out every problem, 9 through 21. So 1, 2, 4 through 6, 9 through 21 odd, 25, 27, 32. Yes. Yeah. And you've got a little over 15 minutes. Okay, so if you need an extra book, I got some up on the shelf you can borrow.